Yeah, that's a problem. It's a little thing that I don't know how to change English. And then now it should be when I start. And then it is posted.
All right, so let's get started. So today we're going to talk about cross-validation and p-values. So I think this is a pretty important lecture. We'll kind of connect a bunch of stuff together, especially if you haven't seen this before. I believe even if you have seen this in other classes, hopefully we'll get some new perspective on this. We'll kind of, towards the end of the lecture, we'll have a kind of a discussion on some of the more vague aspects of these things. But let's start by so let's start by looking at the schedule as usual. This lecture is listed under today. Parts of it are associated with this lecture. I'll probably maybe add half a lecture here, and it'll kind of blend into this later on. I haven't completely decided what to do there. Last Wednesday you turned in hopefully your frequent items assignment. I believe either the grades for those have been posted, or if not, they'll be posted soon. So it's all basically graded. So the nice thing about this homework and everything from here and above is that will be the content of the midterm test, which will be on Wednesday. Okay, so the material we started last week on Monday will not be on. I will not generally ask for that on the midterm. That will be kind of part of the primary focus of the end term test. All right. So you should have. We should have seen the lecture. You have the lecture notes and often topics in the Math for Data book, and then you've done homework assignments on these things and have gotten feedback on the homework assignments. Okay, so you should be fine to take this test. It hasn't changed except the name. I used to call it a quiz. It should not be stuff that is far beyond what we've talked about in class or is clearly defined in the books or we've tested on the homework. It's not necessarily something that you had a specific question on the homework, but it should be something, if I'm going to ask about it, it will be something that we talked about in class and there's some good coverage of it either in the notes or in the book. All right, so if I haven't talked about it in detail in class and it shows up in the book or the notes, probably don't worry too much about it. If I talked about it in class, but it's not really in covered detail in the notes or the book, shouldn't worry too much about it. Everything else is fair game. Okay, it'll be 3 questions. Each question will be a full page and have multiple parts. I don't know exactly what's on it yet because I still haven't made it. So if you ask me, I won't have an answer for you on that. Don't worry, it'll be done on time for Wednesday. So I promise you'll come and you'll have some sort of test to take. And again, you can have one sheet of paper front and back with as many notes of any type as you want on this, but no other notes, no calculators, no computers, no phones. I don't want electronic devices that have potential to kind of send messages. Okay, and so you can bring in some scrap paper and work on scrap paper. That's fine. But there should be. I should design it so there's enough space to work out the answers in the space provided on the pages. So that's how the questions are designed. Some people, it's perfectly reasonable to want more space, and that's no problem. All right, so any general questions about the midterm? Yeah.
Are the questions like stepping through algorithms by hand, comparing and contrasting different algorithms for different techniques? Like what kind of style questions?
Yeah, so that seems like a reasonable style question. Yeah. So it'll be stuff that should not be difficult to complete in the 75 minutes you have. Okay, so it could be working through algorithms. It could be here's input, here's some outputs, which one is correct, explain why, you know, maybe some simple calculations, but nothing that, you know, if you've gotten through middle school, high school math, you should have any trouble kind of doing by hand.
Aside from the notes and homework, is there anywhere we can get like some reference material or examples of the types of questions that will be asked?
So I haven't posted previous versions of the test because I have kind of a cache of sorts of questions which I usually take from those and modify them, and so I don't want to post previous ones. You know, the sort of questions in the homework are not too far outside of the sort of things I'd ask on the test, but they should be narrowed down so it's easy to calculate, right? So instead of a larger data set where you really want to write code to answer it, I might come up with a smaller data set where it makes sense to do it by hand, and you can still do it, right?
So someone is asking online, just wants to double check that the lecture on streaming are included.
Yes, the lecture on streaming is included in the topics. It doesn't guarantee that I will ask a question about it, but I could. Right? I'll ask probably 3 big questions with multiple parts, which means I won't cover everything, right? But it's from here and above, including the streaming lecture, is what we'll include. Yeah. And you should be in class to take the test. So, you know, just to be clear. Okay, so I expect some of you will probably finish in 20 to 30 minutes, and some will take the whole period. You know, that's all of those are fine. It should not be something that requires a lot of work, but you're also welcome to kind of check and double check your answers as much as you want within the 75 minutes of the class. Okay, one more thing coming up, pretty soon after break is the intermediate report for your project. This will be due on the Wednesday after break at noon, okay, instead of earlier. The reason is on this day in class, and I'll talk about this on the Monday after break, so we have a buffer, but just to be prepared, on this day in class, the second half of it I'll break you up into groups of groups and have some discussions amongst yourself to get more feedback. And then soon after this, each group will meet with me. When you meet with me, so when you come to class this day, I want you to bring copies of your intermediate report to share with the other groups. It'll help facilitate the discussion with the other groups to get feedback. Okay, so that's what I want to do by noon on this day, so you have time to print out stuff and kind of organize your thoughts just a little bit more. Okay, if you don't like noon, it can be due at 2:45 on Monday. I figure noon on Wednesday is easier. Okay, so but you should have it should be helpful to have printouts, and when you meet with me later this week or maybe on Monday the following week, bring a printout of that to me as well. I'll talk more about that on Monday, and on Monday we'll have a way for you to sign up your groups to sign up to time with to meet with me at some point one-on-one. There's some dates I think written in the project report about this. Those are still slightly subject to change. I'll work those out over the break, and we'll post something. Okay. So good. So let's talk about cross-validation and p-values. Okay. So let's let's start by kind of getting a sense of the crowd. So how many people have heard of cross-validation before, and who's used cross-validation? Okay, and who's so let's see. So who's heard of so hopefully there's still some new stuff I'll talk about. So who knows? So like some of the pitfalls that where you can think you're using cross-validation right, and you can still, you know, the various ways where you can still leak information into your prediction. I guess that's kind of a vague answer, but vague thing. But we'll talk about some of these issues today. Okay, and so who's heard of so who's heard of p-values before, and who's calculated p-values? All right, so and who's heard of so multiple hypothesis testing? All right, and who's heard of the garden of forking paths issues? Okay. It's just a few of you. So there was a paper I linked off of the notes section today about the garden of forking path, which is some of the pitfalls, including the more advanced ones, included with calculating p-values on data. So these are kind of the two main philosophies on how to evaluate how what you're doing and kind of judge different algorithms and how to compare different techniques against each other, or say if something is significant or is not significant. And they're kind of like, if you took a data mining class like 10 years ago, you would be learning about, there'd be a lot more discussion about false positives and true negatives and type 1 error and type 2 and F1 score, and all these things are kind of important, but they're kind of they're just specific ways of kind of maybe looking at one of these general themes, and there are lots of ways of doing that. So the main kind of underlying philosophy here is that when you have a problem, you're usually given some sort of input, and so we can think of some data set X, and maybe you also have some data set Y, right? So one data point would then be Xi and Yi, where, for instance, you'd say, I think the data incorporated within value Xi allows me to predict a value Yi. Okay, and so this is the basic of the input, but there's an underlying philosophy here that there's some unknown so some truth or underlying phenomena of the world, and how you got this data was that it was drawn by observations of the world, and these observations are IID, right? We talked about this early in the semester. These are all independent of each other, and they're also identically distributed. Okay, so this may not be true, but almost all of data analysis, the understanding of why we think we should use different techniques and the analysis of when something works better than the other, usually assumes some condition like this. So each data point, Xi or Xj, they were drawn independently of each other, and they're both modeling the same sort of phenomena. Okay, and this is important in understanding the meaning behind cross-validation and also p-values. We have this data, which is our input, but really we're trying to understand this unknown distribution mu, which we don't actually have access to. But because we're assumed that the data is drawn IID from this distribution, we can kind of pretend that each data point, we can kind of use this to kind of do special things with this data, assuming that these are IID samples, or kind of break them up in various ways and assume each subset is an ID sample. Okay, so if our setup looks like this, where we have the data, one thing is we often choose some model. And for instance, this simple version would be like so ridge regression. And so there we want to say that associated with this model, usually there's some cost function. Let's say that this is x, y, alpha, where x alpha minus y, right? So this this region regression has a cost function, like what do we call this? S2S, something like this. This is the cost function we're trying to solve. Okay, and it's quite common to have some sort of parameter in this cost function. In this case, it's S. Okay, and so one thing you can use cross-validation to do is to help you choose this value S. Okay, so there are going to be two ways we can use cross-validation. So there are going to be two ways to use cross-validation. One is to choose some parameter, e.g. this value S, right? The other use of cross-validation is to measure so generalization. Okay, what is so generalization? This is the idea that the data has come from this unknown distribution, and if I got a new data point from this unknown distribution, how well do I expect my model to work on this new data point? Okay, and so this is really what we're trying to do, right? The basis of all this is that we don't know this distribution, but we want a model. In this case, the model here is alpha, right? So how well does this model work on new data that we haven't seen before? We can train a model so it's forced to do well on the data we have. In fact, we can fit some models so that it matches exactly, right? But we want it to do well on data we haven't seen before. Okay, and so we can only actually say something about this if we assume the data we have is drawn ID from this unknown distribution. Okay, so we want to say when we get more data from the same distribution, how well is this going to work? And cross-validation can be used to try and evaluate this as well. It can't really do both at the same time. Okay, you can do one or the other, or you can do both, but you have to do them separately. Okay, so you can't use essentially the same data to do both of these things. Otherwise, so I'll explain that issue. So okay, so what is cross-validation? The idea is that you're going to break your data into, I'm going to split x, y into the test part of x, y union the train part of x, y. Okay, so the testing and the training part, and this is going to be a disjoint split here. So if the testing part, these will be drawn randomly, and these are this should be at random. Although it's not so important. If you assume that these are IID, then you could just do it arbitrarily. But sometimes you assume it's ID, but the order may be adversarial. Maybe someone sorted the data before they gave it to you. So you should pick these rows at random. Okay, so this data is going to be the test. and then the rest of the data is going to go into the into the training part. Okay, and so then I'm going to do two steps. I'm going to, one, build model alpha on the test part. And so in the case of, in the example of ridge regression, I can build an alpha star S. Sorry, I'm going to build this on the training part. Okay. Okay, so I'm going to, so I can calculate the optimal alpha star, and basically I'm going to have S, X, train, transpose X, train inverse X transpose train times Y train. So I've got this training data, right, which is going into here, and it's building a model. And then the second part is I'm going to evaluate on the test part, right? So then I can get a score. So I'm going to get a score which is going to be a loss score of X test Y test on alpha star train, right? So I'm going to take the training part in here and the testing part in here. So if I evaluate that, this could be now this loss function of X test alpha train star minus X minus Y test. All right, and this part does not necessarily need this regularization term in here. I may have trained with the regularization term, but I don't need to evaluate it on the regularization term. That was there to help me build a more efficient model. And the regularization term needed this parameter S, and we'll kind of see how this goes. That once I have this evaluation, I can repeat this step 1 and step 2 with a different value of S, right? So if I want to do this to choose a parameter, I can repeat steps 1 and 2 with different values of S, right? Which, yeah, so that should go, not judge space very well here, but there's this plus S squared term that goes into this loss function, okay? Right, so I can plug different values of S into here, and I'm going to get different optimal A star values on the training data. And then each one I can evaluate on separate data here, right, on the test data that I didn't use to do the training on. Okay, and this allows me to evaluate which S value is working the best. Okay, and what's important is that because I assumed all the data was IID, and I randomly selected a subset of it to be the test data, then effectively the test data acts like a random sample from the unknown distribution, and it's a pretty good test of how well it will do on new data, right? I did not use it to build the model, so I can't overfit from special things that I saw there, but I'm going to I can evaluate how well this parameter works. All right, so I can try this for different values of S, and then I can see which one works the best. Yeah?
So are you training with different values of S, or are you testing with different values of S?
So the testing does not need the value S, okay? But in order to plug in a model, I can train this for a particular value of S. right? So I can train this model for a particular value of S here, right? So I train for a particular value of S, right? And with the same training data, I can repeat this training with different values of S, and I can see which one's the best. Okay, so with the if I do the lasso, there's an algorithm called least angle regression, which I just briefly mentioned at the end of lecture on Wednesday, that you basically, in order to calculate it, you calculate for all possible values of S, what the right answer is. And for each of those, as you're calculating, you can evaluate them. In the ridge regression setting, there's a closed form for a fixed value of S. So you would just try a bunch of S's. And then there's a cost function that says, how good does this work? And you want to find the one that is minimizing as a value of S. Okay, and it should probably be fairly convex. There's no specific reason it actually is convex in the value of S, but you can do something kind of like a search over these values until you find like a local minimum. This works pretty well. And if that's not working, if it's not fairly convex, right? So a little bit more space here. Okay, so I can think of having a plot here where on this side I have some cost as a function of the test data and S. For instance, this could be X test alpha star for some value S minus Y test. Right, so this is going to be the y-axis here, and the x-axis will be a different value of S. Okay, and alpha star S will be the solution for the X train and also the value of S. Right, so I'll fix it, and so then what I can do is I can then evaluate the cost function for different values of S, right, and it will probably look something like this. Right, where if I pick too small of a value of S, then I will have too high of a cost. If I pick too large a value of S, I'll have too high of a cost, and somewhere in the middle it's going to be good. And so I can kind of then interpolate in terms of these, and I say, okay, this is the best value of S. Okay, so it's not guaranteed to actually be convex like this, but if it's actually bumpy up and down, it probably doesn't matter so much what the value of S is. It probably means most likely then your data size is probably too small to give you a good estimate, or something else is going on. Okay, but it should probably look something like this in the right value for S. And it may not be as extreme that it looks as parabolic like this. I think, for instance, you'll do something like this on the homework, and it will probably look something like this, where S equals to 0 is not going to do so bad. It will get a little bit better, and then it will start getting worse. Right? So this might be something reasonable that could happen. But there could be other sorts of parameters that you could use here, other than just this case inside of like ridge regression. Okay, so what's something else to see here? If I have this blue curve, there's probably a corresponding red curve that probably looks like this. And this is train on X train and also a test on X train. Right? So if I use the same data to do training and testing, what's going to happen is as I keep increasing S, well, actually, S is only a constraint here. Okay, if I test, yeah, so this might start going up eventually. But what's going to happen is typically, if I test on the training data, I'm going to keep getting better and better past where I'm doing past where I'm doing on the separate testing data. So I'm going to keep improving, but this isn't. That means that there's going to be a gap between where how well I'm going to do on new data and how well I'm doing on the testing data. And I'm probably this regime here. This is like in the region like where you're like overfitting. For instance, if you're doing like polynomial regression, and you're just fitting more and more complex models onto your data, you're increasing the degree of the polynomial, you're going to get smaller and smaller error, and it's never going to start to go back up in this case. You're going to keep getting down to 0 error if you keep trying to evaluate on the training data. And where these are diverging is where you're overfitting. You have too complex of a model at some point. Okay, and somewhere where the testing data starts to go back up, that's probably where you want to stop, because you're saying on new data you aren't going to actually do as well as you think you're doing. Okay, so so there are a couple more questions that you probably have. So the first one might be around so generalization, and this is how well will the model alpha do on so new data. Okay, so if I look at my score on the test data, right? So let's look at X train alpha kind of at S star, and this was on the, sorry, let's do, so if I'm evaluating on the test data, I found my best model with the actual best star on the training data, and then I evaluate, right? So I'm comparing this, so let's say I calculate this, and I divide, say, by this size of the test data, and I can do, didn't mean to draw a line through there. Okay, I can take a square root, and I can look at the average root mean squared error, or if I don't take the square root, that's also fine. That's confusing for you. But I can look at kind of this average error on the test data with the model found on the training data, and I've chosen the optimal S star, the S star which is kind of at the peak here, right? So this is S star. Okay, if I plug that in here, is this going to tell me how well I do on new data, right? If I see a new data point drawn from this ID distribution, and I kind of don't know what the Y value is, and I want to say, well, I can predict what the Y value is, and how good is this going to be? I want to do something like expected value of X drawn from this new data at the Y drawn from this new data minus the model alpha train star using S star on this new data, right? So I can look at this squared, and I want to look at the square root, right? So the expected error, the expected difference from the Y value from what I'm predicting, right? So this is my prediction, right? So this seems to be the right This is y prime hat. This is my prediction. I found a model using my training data. I chose the S star using the testing data. Right? I predicted this model, and now I compare it against this, and look at the expectation of this value over a new data point drawn from this unknown model. Is this going to give me a good answer? Like, can I get that by looking at this quantity? I mean, in principle, it seems like the right thing. I'm taking all my testing data, I'm plugging in my model, I'm seeing on average how well is it working. The problem with this is that this S star is chosen as part of the using the testing data. Okay? So this part S star comes from test. So that means that my entire model, this is the whole model, which plugs into here, includes that S star. Okay, so this is the whole model. This was learned with the X train and X test. Right, so I used the X train to build the alpha part, but then I used X test to build this model parameter, which is part of the model. Okay, so I can't use them both and then say this is a good evaluation of how well I'm going to do, because I'm evaluating on test. It could be that the test data I have biased me towards the wrong S star value. Okay, so this was part of building the model. Okay, so if I want to do, so this is kind of what generalization is supposed to do, but I can't mix it with choosing this model parameter. So basically what I need to do is I have my input data, and I need to pull out this random data, which is the test data, and this goes to give me my S star parameter. I've got this other data, which is going to my training data, and this basically gives me my alpha star. And then I need another set of random data in here, which is to evaluate my generalization, how well I expect to do on new data. Okay, so if your goal is just to build the best model, which is not too unlikely a goal, then you only need to split twice. Okay, I only need to split into two parts, the testing and the training part. But if I also want to take this model that I used the testing data to train the parameter, I need to pull out a third separate part that is used for generalization. Okay, if I want to predict how well I'm going to do on new data. Okay, if I just care about the absolute best model and I don't want to know how well it is, how well it's doing, I don't need this third part, and that's how it's usually talked about. Okay, or I just say I build the model and the training data, and then I use the testing data to do the generalization. That's also talked about. The fact that you may need three parts is often not talked about, and you should be aware of it. Okay. Okay, so then the next question you may have is how to split data. So common ways are, say, 70% train and 30% test, or maybe 90% train and 10% test. Okay, and so the test, what really matters is that the test data is kind of giving you a distributional estimate on one single parameter, right? And so it means you can kind of use one of these concentration of measure bounds, like the Markov, Chebyshev, or Chernoff inequality we talked about at the very start of the semester, to kind of say how accurate is this test. Okay, so how accurate is this test going to be? If 10% of your data is enough to give you a good estimate of that, then that's fine. Use the rest to train, and you can build a more complex model. Okay, the more data you have in the training set, you can build a more complex model. This, like the more, allows a more complex model. And then this allows for better estimation. So, use the Chernoff-Hopting bound to kind of tell you how much that is. Okay, so this is really, this cross-validation approach is really something that has very much taken over in how we generally understand data analysis and evaluate it in the era of very large amounts of data, where if you have a very small amount of data, you really want to put as much of it as you can possibly do into the training phase. And you don't want to kind of not train on some data because you want to leave it for some tests to work hard. If you have 10 data points, putting 3 of them into testing, you're not using that to build a good model, seems kind of wasteful. But if you have 1 million data points, then taking out 10 or 30% is not such a big deal. Okay. There's also a period of time, probably 10, 15 years ago, when a big bottleneck of this was the computational cost of building these things. And you said, well, we finally have enough data, but it's really slow to do this. And so I'm okay actually not using all my training data because it's taking so long to run. We've made a lot of advancements in speeding stuff up, from faster algorithms to also just faster computers and cheaper infrastructure in order to do this on. So that's not really an issue anymore. And if you're building like a deep net or something like that, these can be super complex models. So it used to be that we limited the complexity of the model partially because we didn't have the computational resources in order to actually solve for the right solution. A lot of the stuff we talk about in this course, it involves things which are actually very scalable because we figured out how to scale them up to very large sizes. Like a lot of these deep net models, which are very, very complex, they're still computationally bound. And so that in some sense is limiting, but companies like Google and Amazon, Facebook, which have these computational resources, it's not a limit for them. It may be a limit on your laptop, but not for one of these big companies. So there they want to put as much as they can into the training data, because actually the more data it shows you can build even better and better models. Right? And that's one of the reasons kind of all this learning has advanced so much, because we're building more complex models with more training data. And the amount of testing data you need, it kind of stays, it may not change so much, because if they are really IID, the Chernoff-Hopting bound kind of tells you this somewhat independently of the complexity of the model. So the training data doesn't need to grow that much to really know how well you're doing. If you're getting 1% error, you're getting 1% error on a classification, for instance. And maybe 10,000 data points tells you that, whether or not this was trained on 1 million or 1 billion data points. Okay, so there isn't quite a right answer in the homework. I think you do basically, you'll do like a 33-66 split, roughly. There are other variants of this. One is k-fold cross so validation. And this is, again, usually most useful on smaller data sets where I want to split the data kind of in three ways. So I'll split X into, say, A1, or let's call these, into these subsets, X1, X2, up to Xk. And so then I will, for j equals 1 to k, I will train on x1, x2, xj minus 1, xj plus 1, up to xk, and then I will test on xj, right? So I will leave out one subset, and I'll do this split randomly into these k subsets of basically the same size, and then I will train on each of these on everything except the one set I've held out this data. Okay, and this allows me to essentially not waste any training data, because I'm training multiple models on all of these, and I can kind of average these results in order to build kind of what the best model is. Okay, and I could evaluate S over all k of these different splits. Okay, and each one is a valid test, so the average of them is a valid test. Okay, and I can use this to pick the best S, and so this, and then which model do you use? Well, it's kind of fishy at that point, but you can maybe retrain on kind of on. You can, if you can average the models, if this makes sense, you can do that. If not, the thing people would usually do is they would retrain on all of the data, although really technically you should hold out other data to retrain on. This would just be a way of choosing S in the best way. So you can also use this to do generalization, where the training incorporates the learning of the model parameter. So I hold out another of these to learn the model parameter and train on everything else, and then use this to predict what the generalization is. Okay, so I can also mix and match these things. And so then there's an extreme version of this is leave one out, cross-validation, which is where k equals to n, which is the size of the data set. So I can do this where I test on a single data point. I'm building the model on everything except one data point, and I test on that one data point. This is called leave one out cross-validation. Okay, so this is more expensive. If I do this, I'm running this k times instead of once, the training. I'm running this n times instead of once. So this is more expensive, but if you don't have quite as much data, then this is, I'm not throwing away as much of my training data. Okay, if this is in the regime of big data and I have tons and tons of data, I probably don't need to do this. Okay, this is kind of something that was developed earlier on when there wasn't as much data and people wanted to try and use this cross-validation approach. And so this is a way to squeeze more out of a limited amount of data. If you have a lot of data, you should do this, where I just split it once, or I split it into 3 groups and do that way. That way is safer. If you have enough data, it shouldn't matter too much. Okay. All right, so this works very clearly on something like regression, which is a supervised learning method, where I have some, I have some well-defined cost function that I'm trying to evaluate on, right? If you remember regression, I'm only predicting error on these y values, not on how close I am onto the model, which is kind of like the clustering scenario. And when we talk about dimensionality reduction after the break, that's also going to be an unsupervised method where I don't have labels. If I have labels, this works really well, cross-validation. If I do not have labels, like in the clustering scenario, I can't quite use this to pick a value of k for how many clusters I should have. Because what is the cost function I should be using here? Clearly, as I have more and more clusters, my cost is going to go down, so that's not quite the right thing. If you can make up another cost function, usually it would involve having some label saying these points should be in the same cluster, these points should not be in the same cluster. If you have some data like that, then you can actually do cross-validation to choose k. If you don't have this extra label data, it's not clear how you use this. Okay? But this allows you to kind of build the model and evaluate the model. So I can search over the space of models. All right, so I want to say one more thing about this three-way split about about generalization. There are these. So how many people have looked at like this Kaggle website, right? So I think I linked to it for the class project. There's all these challenges and data sets off there, and the typical setup for one of these Kaggle challenges. This is not always, but typical, is they'll take some initial data and they will split it into three sets, right? There's some part, which is kind of like the training data, which they make completely public with some labels. There's another part, which is the testing part, where they present you the X values, but not the labeled part, okay? And so what they allow you to do is to use the training data to submit a model, and it will give you a score back on the test data, maybe only like once a day. And then at the end of some time period of the competition, they hold out this third data set, like this generalization part, and then they will say who's the winner on this generalization part of the data. Okay, so this is the typical setup. And the reason for it is that you can't just say who is the best score on the testing data, because you can actually learn the testing data by continually probing this over and over again. All right, so there's some researchers a couple years ago kind of actually demonstrated this, where what they did is they said, we're going to use this every test we send into one of these Kaggle competitions. I'm going to use that as one data point and try and use this as a way to just learn the alpha star that works well on the testing data, right? And they basically submitted random models every day, and then took those back. And it wasn't quite random. I think they took like they randomly labeled the test data and then learned on that or something. But they took that and then they learned a meta model which did really well on the test data. They got on the top of the leaderboard. But then on the generalization data, it worked very poorly. And this was basically on purpose, right? That it intentionally learned the testing data but did not generalize. Okay, so if you have a setup like this and you don't hold out this third part to see how well you're going to do, you can actually, and you keep testing over and over again, querying the test set over and over again, you will eventually overfit to the test data, right? So you should really only kind of do one way of trying to learn this model and just do this once. Okay, you should not, right? And so like there are these very common data sets, like there are these like MNIST data set used a lot in like simple computer vision tasks based on these handwritten handwritten numbers that have been pixelized. And there are these other data sets that the research community has studied over and over again. And even though they held out some data which you're not supposed to be the ground truth, when it's supposed to be known, the research community is overfit onto these data sets. So the techniques we know how to do work really well on these data sets, but they don't necessarily work as well on new data sets that aren't in this kind of this types of benchmarks that we've tried to solve. Okay, and so this should be worried about this interaction if you're trying lots and lots of different techniques to try and do well for a fixed training and test set. Okay, you want to, okay, and if you even hold out a generalization set, but use the evaluation on this to guide you how well your different techniques are doing, this is also kind of, it's also a problem. And there's, okay, so there are some ways where people have developed to get around this using ideas from differential privacy, which we'll talk about later on in class, where they only return the evaluation on the generalization or on the test set back with some error, right? They always add some noise into the answer they give you, and this can prevent you from overfitting overall. Okay, well, maybe I'll talk about that when there's a lecture on privacy. I'll kind of mention how this fits in a little bit at that point. Yeah.
Do people ever take a bootstrap type approach and sort of resample who's test, who's training, who's generalization from the same data set as a way to get around that?
Yeah, so bootstrapping is a way to understand kind of the variance inherent in the data, usually with respect to a fixed model. I don't think it really gets around this issue. Yeah, bootstrapping alone is not going to do that. Okay, so let's talk about let's talk just a little bit about p-values. Okay, and this is kind of a related idea that came from statistics, from I think usually attributed to like often attributed to like Fisher from like the early 1900s. Okay, and so I've written up this definition. I copied this from someplace. This is kind of a careful way of saying it, so you can see it. The main specific difference here is that you fix some usually fairly simple model that you understand ahead of time. Okay, I fix a model that has usually some small number of parameters. Okay, and then I have data, and I want to see whether the data fits that particular model or not. Okay, and so I want to say if I fix a model, like so I think that the regression, an example could be regression. For instance, I think that the regression has a coefficient of 1 and 0 offsets, right? I think it's the simplest thing I can think about. Or I think that it has no coefficients, it's just actually the mean. So there's actually no corresponds on the values. I just have the offset parameter, right? And I want to check whether the data is telling me that it's not this simple model, that there's something more interesting going on. I'm not saying that the more interesting model is right, but I'm saying it's different from the very simple model. Okay, and so you can define a very simple model, and then you can observe the data, and you can calculate that the likelihood that you would see data like this given this simple model, and the probability you see data more extreme than what you observed is what's called the p-value. Okay, if I have usually this area that I see something more extreme under the assumption of the initial model. If this is like 0.05, so 5% of the time it's more extreme, usually you say that the data is significant, and that means I can reject this null hypothesis of this simple model of what's going on here. Okay, and so usually if you take a statistics class, you'll learn this with instead of kind of, I mean, you can take, I think there's like a 5,000 or 6,000 level statistics class here where you can take this, where you learn this in kind of the instance of like regression. But in like a lower level statistics class, you'll learn this with respect to like a single parameter function, right? So I have some data. I believe that some data point is distributed by a Gaussian with the fixed mean and standard deviation. That's my null model. And I observe it, it's out here, it's in the tail. What probability is to the right of it in the tail? That's the p-value, right? So the area under this curve would be the p-value here, and if that's less than 10% or 5% or 1%, you might reject the idea that it actually came from the simple model that you had assumed. Okay, so this is a little bit more limiting in that it compares something to a specific baseline model, and it doesn't say how well a new model you might fit to the data is. It just says the simple model is not a good fit. Okay, but this is still a very powerful and an important concept. It's used a lot in evaluating scientific, scientific results. Okay. Okay. So again, who's heard of the multiple hypothesis testing problem? Okay, and who's seen this cartoon, which I'll step through before? Okay, great. So this is a cartoon from from XKCD, which you can look at online. And so this is kind of a demonstration of this problem that comes up a lot in scientific analysis within this when using p-values. And so let's see. There's someone who runs in who thinks that who thinks that jelly beans cause acne. Okay, they go tell scientists you should go investigate, right? And they say, oh well, there's no. They ran a hypothesis test, right? And they said, no, the actual, we took some data, we did experiments, some blind trials, and actually with jelly beans, there was not a p-value. It was greater than 0.05. So it was within what I think might be this basic hypothesis that it does not cause acne. Okay, so they reject it, but then, or they don't reject this null hypothesis. But then they said, wait, I heard it's a certain color of jelly beans that causes it, okay? So then they run a test with purple jelly beans, and they say, no, it still doesn't, purple jelly beans don't cause acne. Run it with brown jelly beans, no. With pink jelly beans, and they'll do this for like 20 different colors, okay? This might not be uncommon, and if you can see that there's one of them in here, that the green jelly beans, the p-value is less than 0.005. Okay, so what will happen then is they publish a paper, it's in the newspaper, green jelly beans cause acne, and you've probably seen news articles that have resulted from something like this. Okay, dietary articles tend to get in the news a lot. They're very hard to run good experiments for, and there are lots of variations of things you can try. And so this is an issue with multiple hypothesis testing. What happened here, they tried 20 different hypotheses, and lo and behold, 1 out of 20 was 5%. 1 out of 20 returned something that should occur less than 5% or less than 1 out of 20 at a time. Right? So this is actually, if you run 20 things, you actually expect one of them to have less than 0.05. A p-value of less than 0.05. Okay, so this is, this is a clean kind of picture of the multiple hypothesis testing problem. Okay, and this occurs, unfortunately, large amount of time in science. Okay, so often what happens is how the modern scientific paradigm works is you have this enormous data, maybe you get to working data, you do data mining, you draw a conclusion. Maybe you do some random trials by generating more data, hold that out and say, it would have fit a basic model less than 5% of the time, and you get a p-value, you do this. I run a bunch of these experiments, right? Or I have, right, so this could happen by generating independent data, and just doing it with a bunch of different types of models. If I try a bunch of different types of models, one might do better than 5% of the time. Now, there's probably correlation between them, so there might be something that saves us there. But if you're doing this with research groups, think of each of these kind of pass through here is a research group that's trying to analyze some data, and maybe they go and they're doing some data on green beans or something. And they grow green beans, and they say if I expose them to sunlight in this way, then I double the amount of green beans. and maybe one of them runs this and they think they produce a better green bean, when really they're just the unlucky one because the data they had fell outside the 95% range, right? And so there was this study came out around 2005 where they found that they looked at a bunch of articles in Science and Nature and tried to reproduce these results, and found that most of them were not reproducible. The ones that tended to get into the top journals in certain areas were ones that were very exciting results that people were surprised to find this result. So that's why it got into the top journal. Turns out they were surprised because they weren't actually true. They just happened to be that the data this lab tested kind of had a small p-value. So this became like a crisis in science. Okay. All right. So there's this statistical technique. So it's called a Bonferroni correction, which is where you can actually, if you know that you did 20 different trials, you should actually essentially, you should divide the threshold for your significance level by a factor of 20. Okay, so now I need it to be less than 0.0025% if I run 20 trials. And this is one way to correction, but this can be overly conservative. Right? And if I'm building kind of a large family of models here, or I'm searching over an infinite family of models, then there isn't really a good way to do this. Right? So if I'm searching model parameters, which is kind of what data mining machine learning is doing, then this doesn't exactly work. Yeah, so that's what I meant to say here. So one approach to this, so this kind of was a crisis in science. What a lot of kind of biological and other sort of research groups started doing is saying, we're going to, like there's this basic setup which you learn in your statistics class. There's this simple unique test that I can apply on the observed data, and I'm just going to test this. This is a safe setting. I'm only trying one model, and I promise to only try one model. Right? There's this other way where I can say, I'm going to pre-choose a set of these tests. Okay, and maybe it's more than one test I'm going to run, but I'm going to do a Bonferroni correction or some other correction on this. And so in science, what they started making available is a way where research groups can pre-publish, I'm going to run this test. It's going to take me 6 months to actually run the test, but they'll run the test, and they'll put that in a database. They might even encrypt it so it's only revealed after they finish the test, so other groups can't scoop them on the idea. But then they pre-publish this test, and if they know other groups are running the test, they can factor that in some way. And again, this is actually going to be safe, right? But I'm only allowing certain types of data transformation. This includes kind of, I'm only going to choose certain values of S in my cross-validation term. Right? I'm not going to choose all of them. I'm only going to choose certain values. Okay? And I'm only going to try certain types of models. I probably can't do something like a deep learning architecture that's learning models. It's not clear how it works with this. Okay, there's a third type, and let's skip to the fourth type. There's clearly a bad type, right? There's this type called p-hacking or phishing, where I'm going to try a bunch of these models, and then I'm going to report the p-value based on the best of them. And I can publish papers this way. And there are people who have done this and gotten papers published, and these eventually later are found kind of not to have a correlation. But you can actually try this and report it as if you only tried one, but only report the best. And this is clearly bad. People do this, but this is clearly bad. But there's this third type, which is in between. And this was pointed out on this Garden of Forking Paths article from a few years ago. And that's where you kind of choose what sort of analysis to do after looking at the data. Okay, so I look at the data. Maybe I plot the data. I say, oh, now that I've plotted the data, I'm going to use linear regression to fit a model instead of clustering. Right? Well, that's already choosing these models based on the data in some way. And that's kind of like trying to use the test data that you chose your S parameter with to predict your generalization. Right? That's kind of the same sort of fallacy going on here. And this is probably pretty common here with p-values. Okay, so if you really hold out your generalization data and you don't look at that until you're all the way done, you're completely satisfied, you're okay, right? But if you don't do that at all, you use the data to decide how to analyze it, and you don't hold out additional data until the end, you're falling into this third trap here. Okay. So these p-values in general are dangerous. Generalization and cross-validation can fall into similar traps. So, all right, so I think I kind of went through this quickly. We covered a lot of stuff. Some of you have probably seen some of this before. But I kind of wanted to leave open some 10 minutes for, say, discussion on what do you think is the right way to deal with this, right? Have you thought of a situation when you've made some decision based on data where now that you think about it, you've fallen into one of these traps?
I've had it explained to me before as rather than coming to a conclusion stating like this correlates to this, you should report your p-value directly and say like, well, I just came up with a p-value of 0.0 something. This p-value may indicate something, and that would kind of prevent sort of like picking a p-value that's good and then just saying, oh, it worked. Like,
Yeah. So that's a good point. So should you actually just say it's significant if it's less than this value, or should you actually report just the p-value, right? So if you report the p-value of, say, 0.04, right, it's less than 0.05, then maybe it seems significant, but then if someone does another round of gathers more data, or they do their own experiment, they can do like a Bonferroni correction between your test and their own test and check whether yours is still significant, right? And so this is definitely a good thing to do. Also, I hope this was not your first exposure to p-values. I probably did not do a great job of explaining them in the short period I had. They can be pretty confusing, and a lot of people use them in incorrect ways, right? They try and justify a model instead of using it to do a rejection on a model. So I think reporting the p-values is good. It doesn't necessarily solve this if you decided to run a particular test after kind of plotting the data and saying it looks like it's Gaussian, or I ran a polynomial fit regression instead of a sparse high-dimensional regression. Yeah.
It seems pretty obvious that we shouldn't put publishing science in news until it's been produced.
Yeah, so should we quit reporting science in the news until it's been reproduced? Yeah, so this is an interesting dilemma, right? Let's say you have a new test that you think is going to cure a certain type of cancer, right? And you run trials, and it seems very effective, right? And they're kind of medical kind of guidelines that if you're running a new thing and the test is clear it's working really poorly, you should stop. Ethically, you should stop it early. And if it's working really well, maybe you should report it and get it in the news, and hopefully that will spur someone to do more, to kind of check this more quickly. So I guess what qualifies the news? Is it like if it's in science but not in like New York Times, where's the line between the news, right? And can you tell New York Times not to talk about an article in science? You know, so like science actually has like a business model. Science, they actually try and make money, and they will talk to newspapers and say, we have a new article coming out, here are the results, don't report on it until this date when the article actually appears. Now, is that the right thing to do? You know, I think that's another issue, but it's a good point. Like, at what point should you not kind of discuss things when you're not sure about them, right? Let's say I ran a hypothesis test and the p-value was 0.000001. You know, I'm pretty confident something's there. But maybe there was a flaw in how I performed the experiment, right? I had some dirt on my microscope or something like that, right? That having another lab look at it independently would kind of avoid these sorts of mistakes.
Yeah, I was kind of chatting with some friends today, and I was thinking, it'd be cool if we could incentivize as a scientific community, like repeat studies more, because that's like not quite, obviously not as prestigious, right, as producing original work.
Yeah.
So maybe we could find a way to like incentivize those studies that we'll go back and like start recreating this stuff, then we'll get more sure of the results of it.
Yeah, that's a good point. So, I mean, that was actually spurred a lot when this article was published. Essentially, the kind of the community started to emphasize reproducing results more. It's still not as glamorous, but there are cases where if I want to build, let's say you come up with a new algorithm, and I think I have an idea to improve upon it. I need to reproduce what you have first. And so this is kind of, the more popular something is, there's some incentive to try and reproduce it, but it's not like just reproducing it by itself is incentivized. And yeah, I wish there was a better way of doing this. But.
So for me, I think all of those questions rely on the fact that null results aren't publishable. And that's like a problem I see in my field is it doesn't matter if you have a bunch of positive results. If you're like trying to just gather data, if you have no examples of things that don't work. And I know there are problems associated with null results. You know, maybe you did the experiment wrong or whatever, but there needs to be more incentive to like really good experimentation that says, hey, look, it just doesn't work as well as it does.
Yeah, so people have started a few journals where you can actually publish stuff like this, and after this, there was this movement to post these experiments online before you ran them, and so some of this has started, but you're right, it's not nearly as glamorous, and a lot of fields don't have a good mechanism for sharing this sort of stuff. One thing, some communities within kind of data analysis, like I think in natural language processing, it's common when you give a presentation at a conference where you're announcing a new technique, you should often discuss the places where the new technique does not work well. And this has become kind of commonplace in some areas. And I think this is a great practice. So if you go out and give a talk at a conference, might be nice to throw a slide in there. People will appreciate this.
Is there like an IEEE collection of standards for best practices regarding scientific experiments, or any sort of like work that's been done on gathering best practices?
I don't know of one. It doesn't mean there aren't standards out there, but I don't know of a clean place to point you to in regard to this. For instance, like this only came out 15 years ago. This fallacies with cross-validation, these came out 3 or 4 years ago. And there's some follow-up papers that had used differential privacy to kind of fix some of these issues. So I mean, some of these issues are fairly new, right? So a guide 5 years ago would not talk about these cross-validation fallacies even. People almost thought that was a panacea in some way for this, and it's not, right? And it's not clear it actually works for deep learning in the way you would expect as well. So there are other sorts of issues in that area as well. Okay, so this is kind of important stuff to think about, right? You may not have all the answers, but try and keep these issues in mind as you go through your careers in doing this. All right, so test on Wednesday, 1 sheet of paper with both sides you can have for notes, but no computers or calculators or phones.